Okay, we continue. And the first task is to remind the tasks of the last lecture. Do you remember? Me not. Yes, even GL2 over itself. The adjoint action of GL2 over itself. So the question was to describe orbits and stabilizer of this adjoint action. So I'm sure you know it very well, but maybe you have not yet formulated this result in this way. We have G2. I prefer C, but if you want R, it's also good. So matrix G, it is just a matrix A, B, C, D, such that the AD minus BC is not equal to 0. And it means that G is invertible. There exists G minus 1. And the adjoint action of GL2 on itself. What does it mean? That we have to construct a map. So in this case, the group and a set, they are the same as a set, but their role are different. So this is an element of the group, and it acts on an element of the set. And this pair is mapped into G minus 1 H G. First task to demonstrate that it is an action. Do you remember what is an action of the group on the set? What to demonstrate? What's the matter?
Isn't it already an adjoint action?
Sorry?
Isn't it already an adjoint action?
This is an adjoint action, but it's the statement. What to prove to demonstrate that it is an action of the group on the set?
Okay, what to prove? Okay.
Yes. So what is this? If you fix G, it maps some H to different elements of the group. Why it's an automorphism? Just this, how to say? It is a joint action of element G on H. Okay? So, and we have to demonstrate that for each J, a joint action is an automorphism of the set G. So it defines a bijective map of the group to itself. Why it is in a bijective map?
We just have to consider H and some other element.
Joint G, it maps H to H prime. Why it is a bijection? Why a joint G is a bijection on the group? Maybe some ideas.
First of all, we can confirm that if we have two images, their pre-images are distinct.
Yeah.
What is the definition of bijection?
Not exactly. It is also should be a surjection. So for each point in here, you can find the preimage. If it is a surjection, embedding. If it is a surjection and if it distinguish different pre-images, then it is a bijection. But there is a simpler way to demonstrate that some map is a bijection, to find its inverse, because each bijection has an inverse map. Maybe you know the inverse?
So it's G times the element times G minus 1. Inverse.
G? Aha.
Yeah, the element that we took G from this group times this H times G inverse 1.
Aha.
Then we calculate it. We should be equal to.
I propose to demonstrate even more general statement that the composition adjoint of G, composition with the adjoint of F, is the adjoint of G multiplied by F. Is it right? Is it right? Maybe it's G, H, FG. So in some sense, it's better to write here inverse signs. Let us work with such a definition. And if so, then it is just the multiplication in the group. So if you verify this, we get all the facts about this action. So it's a homomorphism, and there is an inverse. But is it right, this one?
Yes, it is right.
Please.
So we have to act on an element.
Mm-hmm.
So we act as such as this. Then it's this. Then we use this, which is by definition is the adjoint action of GF on H.
Okay. But could you understand now why this is a bijection? Could you find its inverse?
Yes. So its inverse is, we can notice that this is true.
Yes. Because it's a joint action with respect to the unit element. And unit elements acts as an identity, isomorphism, bijection. Just H to H. It's identity map. Yeah. So that's why this automorphism is inverse to this one. Okay. And we demonstrated that it is also a homomorphism from the group to the group of automorphism. Okay? This is the demonstration. Now we should define the orbits and the stabilizers. Have you some ideas?
So for orbits, not for stabilizers, so by definition, we act on an element H, and we get GH, G minus 1, and so the stabilizers are such G's that this is equal to H, right?
Yeah.
And so have to find all matrices G that compute with H. How do we describe all these matrices G?
I propose to use the Jacobi Jacobi form.
Jacobi form?
The canonical form of the linear operator. Which is the canonical form?
Jacobi decomposition?
No, it's not Jacobi. It's the
Jordan form?
Jordan form. Yes. You know that each matrix can be transferred to the Jordan form by the change of basis. The change of basis is the same as the adjoint action. Is it right?
Yes.
Yes. So you can transform each element by the adjoint action to the Jordan form.
Yes.
Means that in each orbit you can find a Jordan matrix, Jordan canonical matrix. What it could be in GL2?
We're describing orbits.
Yes. You see, in each orbit you can find a Jordan matrix, canonical Jordan matrix.
So we fix the matrix H and then we can. I don't exactly understand the question.
It's a way to distinguish different orbits.
Yes.
So it's one way to do it, to find in each orbit some special elements. Jordan canonical matrix, it's some special matrix. So the statement is that in each orbit you can find a canonical matrix, canonical Jordan matrix. Okay? Could you find different canonical Jordan matrix in one orbit? No. It means that there is a correspondence between orbits and canonical Jordan matrices. And the question is now to parameterize canonical Jordan matrices. What are they in the case of GL2?
So we have matrices such as L1, L2.
Mm-hmm.
These. Also, we have these ones.
Mm-hmm.
And I guess that's it.
You have always the diagonal matrix with coincident diagonal values. Okay. So it means that in this case, lambda 1 and lambda 2 are generic, even coinciding.
Yeah.
Very good. What are the stabilizers of these orbits, of the elements in these orbits? If a matrix lies in such a generic orbit for different lambda 1 and lambda 2. So I propose to distinguish the case of coincident and different. 1 is not equal to lambda 2 and lambda 1 is equal to lambda 2, lambda. What is the stabilizer of the element which lives in such an orbit?
So it's definitely the identity matrix.
Yes.
And,
Yeah, and maybe some other things.
how to describe all of them?
It's an important question. Let us give the exact answer. A generic, it is called semi-simple element. Semi-simple means that it has different eigenvalues. What are the matrices commuting with such a matrix?
So it's basically all the matrices that commute with a sort of diagonal matrix, because its elements are different.
Yeah.
And maybe I've forgotten.
Let's write down just this condition. It is, yes.
So
Just you examine the matrices commuting with the generic diagonal matrix. What are they?
so in this form.
Mm-hmm.
So we just try to. Okay. Which is equal to this, but we do it in reverse.
Do you have an answer?
No, I'm thinking like maybe all the diagonal matrices.
All diagonal satisfied, but are they different matrices?
Yes, maybe yes.
Then we look at this. So A is not fixed. So we have to impose this. The one, and so if lambda 1 and lambda 2 are different, then it means that we have to set B and C equal to 0. So it means that it's just
Two different elements.
yeah. So it's a sort of diagonal matrix with
A?
sort of a diagonal matrix.
What does mean? I don't understand.
Diagonal
Well,
matrix
it's
with
not
two
it's not
different
the,
elements.
it's diagonal. Yes, it's diagonal.
Just diagonal.
Diagonal.
Uh-huh.
I thought diagonal is as in all elements are the same. No, it's
No.
so
No.
it's just diagonal.
Just diagonal.
Yes.
So if you fix a matrix which is diagonal with different eigenvalues,
Mhm.
all matrices commuting with it are just all diagonal matrices.
Yes.
Okay. Could you understand what is the stabilizer in the case of the diagonalizable matrix with different eigenvalues? Not diagonal, but which lies in this orbit.
What are the stabilizers? I think it's also just diagonal matrices.
But diagonal in the basis in which this matrix is diagonal. Okay. Yes, that's right. What is the stabilizer in this case?
All matrices.
All matrices. That's right.
I guess it's GL.
Mhm.
Not all, but
Mhm. In this case.
Similar kind of matrix.
can I check if I have?
Yes, yes.
So these are the same. So in this case, we have to impose these conditions. So we have to set C equal to 0
Mm-hmm.
and this. Here also C equal to 0 and we could D. Yeah, and A equal to D.
Exact.
So it's just upper triangular matrices with
Same diagonal.
yeah with the same.
Mhm. So it tells it's a Jordan block
Yeah.
in the same basis, but maybe with different eigenvalues, with different eigenvalue. Only one eigenvalue because it's a Jordan block. Okay. So we need to represent now all the space GL2 as the disjoint union of orbits. Do you understand what are the dimensions of the orbits? What is the dimension of this orbit? The stabilizer is two-dimensional. It means that you consider quotient with respect to the two-dimensional group.
Why?
And the orbits became two-dimensional. So if you fix two eigenvalues, there is a two-dimensional subspace of matrices with such eigenvalues. Okay? It's an orbit corresponding to this choice of eigenvalues. If you like, it could be presented like this. So there is a two-dimensional part which parameterized by pairs of eigenvalues, and over each part there is an orbit, which is also two-dimensional. Over each point in this parameterizing, I don't know, chart. Okay? Another chart is one-dimensional, this one. Here we fix lambda, but the orbit is zero-dimensional. It is the only point. Okay? Because if it is diagonalizable and the eigenvalues coincide, it is a scalar matrix. And it is preserved by the adjoint action of the whole group. So here the orbits are just zero-dimensional subvarieties, just points. And this is a little bit more interesting. So there is also some slice which is also parameterized, which is one-dimensional, which is parameterized by lambda. But here the orbits are also two-dimensional, as here, dimensional. And this is the orbits of matrices which are represented by the Jordan block with the fixed eigenvalue. Okay, so this representation of all the group, so you see, this is all GL2, see, and it is the disjoint union of orbits of different types. There is one-dimensional space of two-dimensional orbit of Jordan blocks. There is one-dimensional space of trivial orbits of just one-point orbits. And there is a two-dimensional space of two-dimensional orbits of generic elements, of just semi-simple element with fixed eigenvalues, fixed different eigenvalues. Is it clear? So it will be important for us to examine the symplectic structure of Poisson manifold in what follows. So, okay, we described the the orbits of the adjoint action. Thank you very much. I remember another task which was related with the group algebra of the symmetric algebra and its center. Please remind the task. S3. And the question was to describe the center of this associative algebra. But first of all, let's remind what is the group algebra for the finite group.
The group algebra is a space set of sort of polynomials.
Yeah.
And in this case with complex coefficients.
Yeah. So if the generators of our group are G1, which is just a unity, G2, which is the transposition 1, 2, G3, which is the transposition 2, 3, G4, which is the cycle 1, 2, 2, 3, G5, which is the cycle 2, 3, 1, 2, and G6, which is the transposition 1, 3, or I prefer to write it in such a form. Then an element of this group algebra, X, which is Xi, Gi, 1 to 6, Xi are the element of, this is exactly CS3. And the multiplication, the summation of such elements, it's just the summation. So we can consider these elements as the basis in some six-dimensional space over C. There is an operation plus on the space, like in the six-dimensional vector space. But
the dimension of this algebra 6?
yeah, as the space, as the linear space. It is six-dimensional. It is the basis in this space. Each element is represented as the sum of such element. It means that it is a six-dimensional vector space. And more interesting is that on such elements we can define the multiplication. And the question was, what is the center in this algebra with respect to the multiplication? What are the elements which commute with all elements with respect to such a multiplication? For example, an element 1, 2 is not, it is an element of this algebra because it could be considered as 1 multiplied by 1, 2 and 0 multiplied by all other elements. So this is not central. This element is not central.
Once again, what did you check here?
Here,
Yes.
I consider an element 1, 2 of the group as an element of the group algebra, because it's some linear combination of such elements with coefficient 1, 0, 0, 0, 0. Okay? I mean, manifest that this element is not central. There are elements in our group algebra which
Why you took like 1, 0, 0, 0?
So in this notation, it has coordinates 0, 1, 0, 0, 0, 0. Because 1 is with at.
Yeah,
Okay. So obviously this element is central. It commutes with which elements? Yeah. But 1, 2 is not central. Could you propose some other elements which are central? If you don't have ideas, the best way it is to write down in indeterminate coefficients, with indeterminate coefficients. just to write down the generic element and to commute it with all generators.
General element of this.
Yeah.
All general-
With all generators. The generators are elements of our group. So if we find an element which commute with each element here, it will commute with all elements of the group algebra.
That will be central.
It will be central.
So in case of this 1, 2, it's not commute with others.
It doesn't commute with 2, 3, for example,
Yeah, just
because this composition is one cyclic element, and the composition in inverse, it is another rotation. You remember? These elements are just rotation on a two-dimensional space, and these are rotation in different directions. So they're not. It is not the same element. That's why 1, 2 doesn't commute with 2, 3. Okay.
But if we, so it seems like all the generators itself will not commute.
Except unit element.
Yeah, except unit.
But there are linear combinations
Yes,
of.
we need to do some linear
Yes.
combinations.
I propose just to consider the generic linear combination and to verify, to find the condition on coefficients guaranteeing the commutativity. There is another elegant way to do it, but it is always better to do something.
Seems like
Do you understand?
1, 3 also. Where is 1, 3?
Okay, 1, 3 it is this element,
Ah, yeah. Okay.
but in some sense it's better to represent it like this in terms of the set of generators. So these two transpositions, they generate all the symmetric group. Okay, just by composing this transposition, you can obtain all elements. 1, 3, in a sense, it is derived. It is derived from these two generators. Do you like to make it at the
Yes.
black box?
I can
We will help you. Don't worry.
So, so first thing we need to do is make a linear combination of the generators.
Yeah.
So the generic idea I can see is this plus this, say 1, 2 plus 2, 3.
Mm-hmm.
So this also has like 2 elements, so maybe we can plus. This.
As you like. You can write 1, 3.
Yes, something like that.
Uh-huh.
Now we need to check that if it commutes with what?
With all elements.
With other elements.
Yes.
And what we need to do here with this is to write the coefficients over here, right?
Yes.
And so how can we check it?
But why you have written only 3 elements? In the group, we have 6 elements.
Yeah, well, my choice was like, so they have 2 here, so I just like 2, so maybe there are 2 guys over here, we can write like this also and check. And check with others which have 3, so it's like maybe guessing idea, but...
You see, it's right. So this element is central.
Okay.
But we have to demonstrate it. So we have to commute this element, but in fact, it is sufficient to consider its commutator only with generators. Because if it commutes with generators, it will commute with all elements.
Yes, yes.
Because all other elements are just the products of generators.
Yes, yes.
Okay?
So now we need to commute, find commutator of this with, let's say, 1, 2. Maybe.
Yeah.
So
You see, if you will calculate a commutator, it's better to represent 1, 3 in this form.
okay.
And moreover, sometimes we need to know that it is the same as this. Mm-hmm.
So now, if we find the commutator,
Mm-hmm.
it will be with 1, 2, 1, 2, right?
Mm-hmm.
Something like this, right?
Mm-hmm.
We do 1, 2, 1, 2, plus with this,
Mm-hmm.
2, 3, 1, 2,
Mm-hmm.
plus 1, 2, 2, 3, 1, 2, like this.
Uh-huh. Very good.
Minus. So this will cancel. This will also cancel, and this will
Please write. It's always good to write it completely.
1, 2, minus 1, 2, 2, 3,
Mm-hmm.
minus 1, 2, 1, 2, 2, 3, 1, 2. Yes.
Mm-hmm.
So this and this will cancel.
Okay. It's a unit element in both cases.
Yes. Yes.
1,
yes.
1. Mm-hmm.
This will also cancel.
No.
Mm,
You see, these are cycles in different
rotation.
yes,
Yes,
in different directions.
rotation.
Uh-huh.
So in this case, what do we need to?
But here you know it's involutive. So 1, 1 square is 1.
Yes. So
1,
we can
2
like-
square is 1.
Yes. So we can like remove it, for example. For
Just this. Uh-huh. Uh-huh. Mm-hmm. And now
Okay.
they
now-
cancel.
Yeah. Yes. 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 Okay. So now this and this will cancel. This and
Uh-huh.
this will cancel. So 0.
Very good. With 2 free, please.
1, 2, 3.
Mhm.
The same. Let me do for here. 1, 2, 2, 3, plus 2, 3, 2, 3, plus 1, 2, 2, 3, 1, 2, 2, 3, minus 2, 3, 1, 2,
1. Yes.
2, 3.
No. This one. What is?
So it's like
Uh-huh.
2, 3.
Okay.
and 1.
Okay. Uh-huh. Uh-huh.
And then 1, 2, 2, 3, 1, 2. So this cancels.
You have to use this equality.
So
Uh-huh.
this thing is this.
Yeah.
2, 3, 1, 2, 2, 3.
Mm-hmm.
Here also. 2, 3, 1, 2, 2, 3. And then we see that
Mm-hmm.
this cancels, and this cancels,
Very good.
and we have this, and this.
Perfect.
So we can say that this combination is a generator. Center.
Central element. Mhm. So we now know 2 central elements. The unit element
Yeah.
is central,
And this
and this one is
Is also
also central. Do you have ideas if there are other central elements?
maybe we can. So as was my guess was like plus this and check.
Yes. Please try.
if it's worked, then it will work. If it's not worked, then we should cancel the idea. I mean, that is how. So 2, 3, 2, 3 cancels, but here it's also cancel. So it's also a generator.
Mm-hmm.
So it means like if we put here 1, 3 or 2, 3, it will also commute. So we got 3 generators for now.
Yeah.
So maybe we can write this. So 1, 2, plus 1, 2, plus 2, 3, plus 1, 3, plus 1, 2, 2, 3, and this. Are there any more?
No, there are no other central elements, and the general statement is that all central elements are generated by the conjugacy classes in finite groups.
Well, what is conjugacy class?
The elements which are conjugated in the group, which lie in the same orbit with respect to the adjoint action of the group.
Okay.
The conjugacy classes, as in the case of GL2, which we have discussed, they are just the orbits of the adjoint action. Remember? So these elements lie in the same orbits in the group S3. So if you conjugate a transposition by any transposition, you get another transpositions. Okay?
So
If you conjugate a cycle, a rotation by a transposition, you also obtain a cycle.
Yes. Symmetric.
Yes. So in the case of the symmetric group, it is also it's a general statement, but you can obtain this definition just by considering a generic element with all different x, I, and just considering the commutator with generators, with 2 generators. We will get some relations on the coefficients.
And then it will tell us...
It will tell us that we should take the element x I, x1, x2, 1, 2, plus 2, 3, 2, 1, 3, and plus x3, 1, 2, 2, 3, plus 2, 3, 1, 2. So you will obtain the relation that coefficients here and here are equal, and all these coefficients are equal.
Yes.
And that's all.
Okay.
Thank you very much. But please remember this example. It will work in some subject of our program. Okay. Now we will work out some properties of the Kirillov constant Lee Poisson bracket on GLN. So let us recall that we consider the symmetric algebra of GLN, which is the space of polynomials with monomials which are just generators I and J 1n, and we have the Poisson structure on this. So EIJ, EKL, EIL, delta Kj minus EKJ, delta EL. And then we expand this two monomials of all degrees by the Leibniz rule. This is the Poisson structure.
Structure on the G
On the symmetric algebra, symmetric tensor algebra of the vector space GLN.
Okay.
Vector space GLN, it is n by n square dimensional vector space. If you just consider the monomials on the letters which are generators of this algebra, it is the symmetric algebra of this vector space. But on this polynomial algebra, we get additional structure, which is the Poisson structure. The first task in this direction, if n is equal to, so we always consider GL2. It is four-dimensional, but you see it's four-dimensional space, and we get the Poisson structure on it. Definition. A Casimir function on Poisson manifold is function f on C m such that for all h f is equal 0. The synonym of this notion is that it is the central element, the Poisson central element. Definition.
There's another way to check the center of
A Poisson center of Cm is the set of all Casimir function, is the space of all Casimir function. Functions. Your task is to define, to find all Casimir functions.
it's like a symmetric function with a degree up to 2, right?
No, all functions.
But first of all, what is Casimir function? As I know, like it's a symmetric function, polynomial with degree 2. I mean,
No. Why degree 2? Of all degrees.
Ah,
But on 4 variables.
on 4 variables.
Yes, we had a 4-dimensional space.
Okay.
And we can see the polynomials of all degrees on a 4-dimensional space.
Okay.
So whatever you want, the polynomials on 4 variables.
Now we can write an ansatz for the Casimir function and find the Poisson bracket with this h and the element of the algebra which gives 0.
Yeah. So you understand that it is very close to the previous question, but in different context. So now you we have to find the Casimir functions. Very important observation that if you find a function f center, Poisson center of Cm, and f is the sum of homogeneous components, fi homogeneous components. Homogeneous means that they,
Degree same.
yes, or they are polynomials of the fixed degree. So if f is central, Poisson central, and it is the sum of homogeneous components, then fi are also Casimirs. But in our case, I'm sorry, in our case, not in general, but in our case, and S Gillen. Yes, it is very important. Do you have ideas?
Well, my idea was to write an ansatz for this Casimir function and find the Poisson bracket using that rule up here.
Yeah.
If it gives 0, then to give, I mean, we need this to be 0, and then we can fulfill the ansatz with these conditions.
Okay, but why this expansion on the homogeneous components is important? So why, if the sum lies in the center, the summand, the homogeneous summand, lies in the center? It is not always true, but in this case, for this bracket, this is true. Okay.
I mean, I think maybe to get 0, it has some relation, I mean, with the homogeneous polynomials that...
Okay, let us represent our symmetric tensor algebra as the sum of its homogeneous components. Sum over k, 0 to infinity. Okay? So here we consider only polynomials of degree k. Okay? Statement. Lemma. K Gillen Sm Gillen lies in Sk plus m minus 1. So if you consider a polynomial of degree k and a polynomial of degree m, the Poisson bracket is the polynomial of such a degree. Is it close to be clear? That's true for the linear polynomials. It's a polynomial of degree 1, polynomial of degree 1. The Poisson bracket is a polynomial of degree 1. And then this proposition can be proved by induction using the Leibniz rule. You see, when in the Leibniz rule you apply the Poisson bracket, you always make these calculations on the degrees.
Yes.
Okay, so it's quite evident. Then, if we have a central element which is the sum of homogeneous components, we can calculate its Poisson bracket of f with generators. Okay, it is the sum over I fi kl. I would say that this summand lie in different homogeneous components. So if it is 0, then this summand lie in different homogeneous components. So this summand lies in Si of GLN. Fi lies in Si. And the Poisson bracket with linear function lie in the same in the same homogeneous component. So different summand here lie in different homogeneous components. That's why if the sum is 0, then all summands are 0. You understand?
Yes.
So it's an instrument to examine the center of this Poisson algebra. So we have it simplifies our research. So we have to find central elements in each homogeneous components, and it's natural to start.
If 0, then okay.
Yes. So we start by linear and quadratic and third order terms. Please find all central elements in the homogeneous components of degree 1.
It's like x1, x2, x3, x4.
Yes.
And we can check that if we do this Poisson bracket, it will be.
Yeah. Yeah.
So what is our age here? Which is the just the identity one.
H.
So what I told that my guess was like x1 plus x2 plus x3 plus x4. Now I need to check it. What I check?
No. You see now our spaces for n equal 2. We have two linear elements. I'm sorry, 4 linear elements. And the homogeneous linear function in our algebra, it is generic linear combination of these.
Yes.
So we have to consider x1, x11, x12, 21 plus x22, 22. No, x. And we should check that x with eij gives 0 for all I and j. And it's a way to find the coefficients.
I'm not quite understand. What could be the value of the coefficients x11, x12, x21? Are there any real numbers, values for that?
Yes. There are very strict conditions on. The linear part of the center is two-dimensional. So there is a two-dimensional subspace of linear functions which lie in the center. No, I'm sorry, one-dimensional, only one-dimensional. The linear part of the center is one-dimensional.
It's only one element.
Yeah. One-dimensional subspace. You understand, you can always multiply by a constant. There is one-dimensional central subspace in the linear homogeneous component.
What if all these coefficients are 1 or any real number?
But you have just to write 4 equations and try to solve. I claim that the solution, the space of solution is one-dimensional. So you can find only one function and all its linear, all its proportional functions. Would you like to write this problem on the blackboard? We'll help you, obviously. Please. So just try to write this condition. So this is X. It is generic linear combination of generators, and just to write this commutator. These are 4 equations. Yes. Let us start with the first one, the commutator with E11. here I'll say x11. Mm-hmm.
Should be 1.
No, it is the commutator with E11 always. Uh-huh. I think we need just to write it down without sum. Yes, and try to calculate it, because we know the Poisson bracket of. No, just like this, without indices. X1, x12, E12, x21, E21. Mm-hmm. 1, 2. Mm-hmm. Yeah, just this sum with E1. Perfect. X21, E21. Very good. One. Mm-hmm. Now you see that the Poisson bracket is linear with respect to multiplication by scalars. Okay, these are scalars.
So like here rewrite.
No, just right here. X11, E11, E11. You know that it is 0.
Yes.
Uh-huh.
And for the others.
Yeah. X12. Uh-huh. Do you remember what is the Poisson bracket? Okay.
It's the function. Kronecker symbol. I think.
Mm-hmm.
Two gives only the first one is
Minus.
No, I like to say that this is minus E12. And x, minus x12, E12. Mm-hmm. Plus. Mm-hmm. Zero. Okay, and this should be 0. Yeah? Because we are looking for the central element. It should commute, Poisson commute with E11. And the necessary condition that this is 0. But these are different basis elements in. Okay? If it is 0, then both these coefficients are 0.
Cannot we take it like -1? No.
No.
Yes.
They are different basis elements.
Yes.
Both should be 0.
Yes.
Okay, it's a big much information about our central elements. Let us calculate the commutator with E12. Mm-hmm. It means that we consider only the diagonal elements. Okay, this one does not fit our task. No. Okay. Uh-huh. I don't understand. No, we should consider this linear combination.
Yes. Like
These coefficients are zero, or trivial, but these coefficients we don't know. x11, e11, plus. No, plus. Здрасте. x22, e22. With e22. e12, it's maybe better.
I just found that.
Comma here. Very good. This is e11. No, here e22. You are right. It's a correct answer. But what does it mean?
So
Yeah. Yep. No.
I've already found it. No need to do anything.
No, 1, 1. 1. No. Here is 1, 1. But now we change the generator with which we commute. 2.
this one is
0. Both.
minus.
Do you think about the first or the second Poisson bracket? Second is 0 because our bracket is skew-symmetric. If you put the same argument, you get 0. Okay? So what is the answer? This is also 0. And the rest is the element 2, 1, if I understand well. So we have to verify such a bracket E11 plus E22 with E21. Is it 0? 2, 1, 1, 1, 2, 1. Yes, but why it's 0?
Well, by definition.
But they are not trivial.
No, it's not.
No. 1, 1, E2, 1. It is not 0.
Yes, but like
Could you write what is this? And E2, 2, E2, 1. I'm sorry.
But I wanted to ask you, like, we have already verified the diagonal elements, right? That they are equal and they are 0. And this check will also give that they are equal. So same thing is repeating.
Yes. Now we demonstrated that this sum of diagonal elements commute with all generators. And only such a linear combination lie in the center. Okay? So we have found the homogeneous components of degree 1 in the center, in the Poisson center of our algebra. Okay? Just wait a moment. It is useful to organize the generators of our Poisson algebra into a matrix. Just if I write like this: 1, 2, E2, 1, E2, 2. For the moment, it's a formal expression. So these are functions on our Poisson manifold, and I like to organize them into the matrix. I have the right to do it. Okay? So this central element, E1, is the trace of the matrix L. Do you agree?
Yes.
I like to propose you a hypothesis that the determinant of matrix L is also central.
so just calculate determinant and commute bits.
Yeah, in that case, we can check it also.
Yes, just to check.
And the determinant taking the elements of the
With,
Mhm.
algebra.
with all the false or just one. Like,
With all elements. We have to use the Leibniz rule. You understand?
yes.
Mhm.
Or it's like two gives.
Uh-huh. Very good. So you consider it the Poisson bracket of... No, without this Poisson. Uh-huh. There's only one Poisson bracket. But there are two summands. You see, when you consider the Poisson bracket of this monomial with these generators, it's better to write it completely. It's E1, 1, and the Poisson bracket of this one with this one. Okay? And then to proceed to the second. Mm-hmm. Mm-hmm. 1, 2, E1, 2. The Poisson bracket of E2, 1 with E1, 1. Uh-huh. Uh-huh. E2, 1 with E1, 1. Uh-huh. And here E1, 2. No. The Poisson bracket of these two elements, and this will be out of the bracket. Minus this E2, 1, E1, 2, E1, 2, E1, 1. So you consider it this, and now you have to consider this Poisson bracket. E2, 1, E1, 1. Uh-huh. And the element E1, 2 will be out of the bracket. Uh-huh. So these brackets are 0. Okay? Because the commutator of diagonal matrices. One, two. Mm-hmm. No, minus. Zero. Very good. Okay, thank you very much. Our time is finished. So please sit down. Take a seat. Tasks. First, to finish this calculation. To finish the description of the Poisson center of SGL2 in degree 2, degree in the homogeneous degree, you understand? Second task is to find the Poisson center of R2n with the standard Poisson structure. Poisson structure. You remember the Poisson structure we have started with?
Lectures.
Yeah. Just derivative on P minus derivative on P, derivative on Q at the beginning of the lecture. And the third task will be to describe Hamiltonian dynamics also from the beginning of our lecture, Hamiltonian dynamics on S of GL2 with H equal EIJ. Remember, the Hamiltonian dynamics is defined by a Hamiltonian, by function. So let us consider linear function, just the generators of our Lie algebra, to write down the Hamiltonian equation, and let's try to solve it. Okay? Have a nice continuation, and see you next week.